All right. Thanks for being here. Happy Thursday before the Easter break. That doesn't really mean anything for us because we're Tuesday, Thursday. But hopefully if you have Friday or Monday classes that you get a little bit of a break. I'll make sure you give your inheritance packets to me today if you are ready, or give them to me on Tuesday if you're not ready. I'm gonna go through these, and instead of like by completion, did you do it? I'm gonna be looking at your answers to make sure that you're understanding things. So just be aware of that. So if you don't have things marked down, I will grade you down. Lab 5 is due by tonight, so make sure you get that in. I know it was kind of quiet in here last time, so make sure if you are working in groups, make sure everyone knows what's going on.
See. Our team's lab 5, right?
I believe so. Yeah, if you submitted it, then I've got it. Reminder, we do have a project, and you need to tell me who's in your group by tomorrow. So send me an email and say, this is our team name. Our team name is creative name here. And our group members are me and person A and person B. So send me that email. If you don't have a team, I'll show that again once I'm not recording, and you can figure out who has left to join a team and do that. Teams of up to 3, or you could work alone if you really feel like it, but it's a lot of work, so I do not recommend working alone. Okay, our plan is we're going to start our new unit on data structures. We don't have a packet for this unit. Yeah, partially because I ran out of time, partially because I have other activities for us planned. So we're going to talk about linked lists, kind of conceptually how they work, and then we're going to do something a little bit different today. We're going to do a little of a code review based on the lab, based on lab 6. So there's a link to that in one of the assignments. So I'll show you the assignment we do today. That's here. I also just remembered that I didn't upload the slides, so I will do that momentarily. But here we've got a link to some code. You don't have to clone the lab right now. I recommend not cloning the lab because I'm gonna make some changes to the instructions. I'm gonna make the instructions a little bit clearer. But today we just need to know the link to like the code. So you're just going to be reading the code today. So no cloning required. You can if you want to, but I'm going to make changes. So just be aware of that. Okay, that's the plan. I'm going to pause for a second and upload the slides. All right, let's get started. All right, so we're going to talk about something called linked lists. So far in this class, we started with some scripting for how do we do things in Java. Then we talked about how do we get input from the user, from the command line. And then we looked at classes, inheritance, object-oriented programming, all that fun stuff. Now we have to look at how we create data structures. So now that we know how to create classes and do this inheritance, we can create some pretty complex things. And so we're going to practice doing that. So a data structure is some sort of object that we create in code. So it's typically going to model something that's useful for us in some way. So either we're modeling some shapes, and so we've got classes for shapes and got that whole hierarchy, or we do something maybe that's more like less real world apparent and more just a structure that helps us do our software engineering thing. So a data structure is an object that we create, and we as the programmers, as the engineers, are defining its properties and behaviors. And so this is an image of an abstract data type where we've got our public functions, maybe some private functions that the user doesn't get to access, but that we can still define. And then there's some data structures that we use to actually hold the data and manipulate it or handle it however our data type needs to. So there's two options here. So there's more options also. It's more than just array and linked list. But typically our main base data structures are arrays or linked lists. Luckily, we know what arrays are, right? They're these contiguous spaces in memory that hold information. We haven't talked about linked lists yet, so we're going to talk about that. In this, I want you to remember that we are the designers. So we're going to talk about a common data structure that's well known throughout computing called linked list. And so we're going to see here's how this data structure typically works. As we go through, keep in mind that there are assumptions that are made. And so it could be if you were going to design a linked list class from scratch, you could have made different assumptions. So this is the key that I want to impart to you, where we're the designers here. I'm going to show you an example where we make some assumptions. You could have made different assumptions. So a linked list at its core, we're going to define I'm going to show you here's the linked list class. And for our activity, you're going to read through it and basically outline. Here's what this does. So if I give you some code, then you read it and figure out what's going on. This is an important skill because if you go into industry, chances are you're not going to be starting with a blank slate, right? Someone's going to be like, here, I have this project, it's already partly done. Do this thing. And so you're going to be given all this code and you have to figure out how to read it, what's going on, and figure out what am I supposed to do in this. So I think this is going to be a useful activity to help you practice reading code, figuring out what's going on. So the data structure we're looking at is a linked list. It's kind of like an array in that it stores items typically in a linear fashion. So an array, typically we draw it as just like this big long rectangle where all this data is one right after the other. A linked list looks a little bit different. So I have some pictures that I got from the internet. They're from different sources to kind of give you a broad overview of how we typically draw it. Let me show you how I draw it. I tend to draw it as like these separate boxes. So whereas an array, it's all one big long rectangle that we divvy up into slots. A linked list, each slot is its own box. And so we say this, so for this box is 0th, this box is first, this box is second, and so on for an array. In a linked list, we say this is the 0th box, this is the first box, this is the second box. And the way that we connect them together is through arrows. So the 0th box points to the first box, points to the second box. That's pretty much how we draw it. So let's look at, so this is the basic idea of what you'll see going forward. Okay. So I'm going to give you an analogy for how this works. So let's say we've got this river picture, but let's imagine that it's really dark instead. So here it's daylight. You can see the path. You can see the grass at the other end of the river. But let's imagine that it's dark, it's night.
And we don't have night vision goggles.
And we don't have night vision goggles, exactly. So there are stepping stones to help guide us across, but it's so dark that we can only see the next step. So we can't see 2 steps ahead or 3 or 4 or whatever. We can only see right in front of us, right? Maybe we've got like a really, really bad flashlight or something. And so we're making sure that we're not about to step in the water. So we can only see the next stone. And I like this picture because these are kind of, the stones are kind of small. And so if you're standing on this small stepping stone, there's no really real way to turn around and look behind you without falling into the water. So we can't look back either. We can only look forward. We can only move forward. That's the basic idea. That's the most basic implementation of a linked list. So a linked list is made of, it's kind of, so we've got building blocks where if this is a linked list where one box points to another, we have the basic building block of a single box, right? So if this is our list as a whole, the box itself is a building block. And so this box is called a node. That's what we call it. And so this node contains some data, and it contains a pointer or a reference. And remember when we talked about reference variables, how like for an int, the data is stored in that spot. But for a reference variable, the variable points to somewhere else in memory where this information is stored. That's the idea here, where we've got this reference, and so it's some variable that points somewhere else. In this case, it's going to point to the next node in our list. So this pointer, here, let me redraw this. So we've got some data. Typically, I'll show it as like segments. So this is our data. Maybe we've got a shape here. Maybe it's a triangle. And we have a pointer, which in the simplest application of linked lists is just we're pointing to the next thing in the list. So we'll call it next. And we represent that by having an arrow point from this thing out somewhere. So either a pointer points to something, so maybe it points to another node, or an arrow goes nowhere, where it points to null. And so you'll typically see that drawn as either just an arrow that points nothing, or an arrow points to maybe there's lines after it. Then that signifies null. Okay, so that's a node, which has data and a reference, a pointer. That's our basic building block. And so the list as a whole is this set of nodes and references. So if we have one node after another, where one node points to the next, then we've got ourselves a linked list. I wish I had this picture at the beginning, but I want to skip down to the end because I want to show it. So did you ever make the paper chains in elementary school or arts and crafts? That's kind of what it's like, right? Where we've got some starting points and we connect each chain to the next, to the next, to the next, to the next, until we get to the end. And that's, yeah. So each one connects. And so each node is this individual loop. And so when they intersect, then they're all together, they're part of the linked list. If there's one just off to the side, that just like one circle by itself, then that's not part of the list, right? It's not part of this chain. Okay, let's go back. All right, so we'll go over an example that is singly linked. So singly meaning single meaning one, which each node is only going to have one reference here. There's also situations where there's other configurations. So there's like a doubly linked list where we change how the node class is defined. Remember, we're the designers. We could say that instead of just one pointer to go forward, we can also go backwards. So we could have something that goes forward and backwards. And if we chain together a list of doubly linked nodes, that gives us a doubly linked list. So the example we're going to look at, the code is singly linked, but we could change it so that it could be a doubly linked list. In addition, if we're working with data that needs this structure, we can have as many links as we need. So however many we need, we just need to define that node class accordingly. So we're the designers, we could change it. And we'll look at the basic operations for how to insert things into our list, how to delete things in our list. So we'll go over those. And then there's some other operations that I'll leave you to decipher in the code. Okay, so we talked about this. Maybe I should have put this slide before the other one. Oh, well. But these are the different ways we can draw it, right? So at its core, we pretty much just draw it as like a box where it has some data. So in this example, it's numbers. We're storing numbers. In this example, we're storing letters. Basically, any sort of thing that we want to, like if we had people in our array, we could have people in our linked list, right? It's just a place to store stuff. It has pointers or references. So here it calls the reference address. So this is saying, here's the memory address where the next one lives at. This one calls it a pointer, saying this is the node after this one. This one calls it next, which I do in my code. So that's what you'll see. But we can call it different things. It all pretty much means the same. Yeah, so sometimes we could have previous. So like if we added a field onto here. So these are fields, by the way. So the data is a field and the pointer is a field. And so we could add another field that points to the previous node. The methods that you'll see get next and set next. So maybe we choose to make these public. If they're not public, then you would need to access them by their methods, right? So if data was private and address was private, then you would need to, the way you access the data is say get data. The way you set the data is with set data. So just keep that in mind. The node is also going to be generic. So we had to kind of skip over genericity for time's sake, but I'm going to give you like the, where's that? Where did I put that? No. Okay, it's all the way at the end. Let's talk about it now. Sorry about that. So let me show you the node code. Okay, so that's LL. So this is the code for node. There is this angle bracket capital T inside. That basically means we want our node to store any kind of data, right? We don't want to hard code that our node is only going to store integers or is only going to store a person. We want to make it as generic as possible because this is a container that we may want to use in a lot of different places. So the way that we do that is it's called parameterization. We parameterize node by some variable that we call T. And so Java knows that when we do this, we're saying some sort of data is going to be stored in here. I don't know what it is yet. The user is going to define it when we get there. And so, yeah, so we've got our data, which is of type T, because we don't know what type it is. We're just going to call that type T because we have to put something when we're writing this. And then it points to another node. So that's our reference because each node points to another node. And so the type of the next field is another node. The way we say that is node angle bracket T to say, I'm pointing to a node that contains the same type as whatever I'm holding. So if I'm holding a shape, the next node's also going to hold a shape. So then we've got our constructors. So we've got our 0 parameter constructor that's set up for null. So if we don't have anything, just create an empty node. No. We've got a constructor. So if we have some data that we set at that, another constructor that if we are given some data and where it points to, then we set both those up. And then for the rest of it, the getters and setters are standard. And just to point out that we are using that capital T type to say whatever kind of thing lives in my node, I'm just going to call it T. Let me show you what that looks like in action. So let's see list demo. I don't know that I create an actual node. I'll just say that, so we'll talk about linked list, but linked list is also parameterized with T to say that whatever goes in my list, it's all going to have the same type. So everything in my list is going to be a student, or everything in my list is going to be a circle. And so we do that parameterization there too. So we make our linked list class generic as well. And so in terms of how we actually use it, so in the lab, we've got a list of computers. And so I define the computer type. And when I create my list of computers, it's like, you remember how we create an array list where we have to say, here's what sort of thing is going in the array list? This is the same kind. This is how that works. So we say, I want to create a thing called list1. It's going to be an LL, and it's going to contain computers. And so that's how I define that. So that's my brief tangent on what you missed in genericity. That's why the capital T is there. That's what's going on. Any questions on that before we go forward? The next slide. Okay, so we've talked about that. So I cropped each of these to give you, these are what a node looks like. So now, in general, this is our linked list. It's just a bunch of nodes strung together. It's our paper chain where we join each of the rings. And so we have our data. So in here, the data is blue and the reference is green. And so each reference points to the next, points to the next. And here they draw to say that this node points to nothing with an X there. This one shows the difference between an array on the left and a linked list on the right. So in memory, an array lives all at the same place, one spot right after the other. That's how arrays work, where we can access them by index, and then they live at these specified memory locations. That's not true with linked lists. So we do not have easy index access for linked lists, where if we've got this array, we could say, give me index 4, and it would give us 95 easy. We can't do that with linked list. We have to compute that. So with linked list, we know where to start. So we'll have something called the head of the list, which is like if you're remember, like, if you line up in elementary school, someone's at the head of the line, they're in charge of leading everyone. That's how we know where the linked list starts. So that we have a node at the head of the list, and that's our anchor point. And so these they live anywhere in memory. So we don't have anything fixed there. They're kind of they can be all over the place. We just need to know where to start. And that means because they're not structured like this in an array, we can't use indices as easily. Okay, this is another way to draw it, where again, we've got the head of the list, so where to start, and then points one to the other until we point to null. So there's nothing left. Okay, so these are my compare and contrast slides, where arrays, we can access it by index immediately because we know where the array lives, and so we can just add the address for that. For linked lists, we need to do something called, we need to iterate through it in order to find that index. So we can still access things by index, we just can't do it instantaneously. And so you'll find that we can't say like linked list square bracket I, sad face, we can't do that. We need to use a method instead, and we need to define what that method looks like. Array's got a fixed space in memory. Linked list is not fixed in memory. That's this one, where it's not as structured, it's all over the place. And so since array has a fixed space, we need to reallocate, so define a new array and make it bigger if we need to increase the size. But for a linked list, since they're not fixed in memory, we can just add a new one, no problem. So say I'm adding another node, big whoop, not a big deal. Okay, so we've talked about this. So the way that we refer to a given node is a reference or a pointer that says, this is especially how we're going to iterate through the list. So where if we start at the top of the list, and let's say we want to go to index 3. And so if we start at index 0, the way that we go through this is going to, we start at the beginning, and that says, okay, I'm at the beginning of the list. And then we can have this variable that takes the links, so that goes from one to the other. Yeah, sorry. So the way that we take the link, so let's say we have some variable, you'll see it as like CURR or current, both current, like here's where we're at right now. Sometimes you'll see temp, TMP, or temporary to say this is where we're at right now. And so if I start temp at the head, then to move, so let's say temp is here, to move temp over here to 42, I do something like temp is equal to temp dot get next. I swear I have a slide for this. We'll get there later. And
We actually writing code.
are we actually writing code? Not at the moment. We're talking about this conceptually. So yeah, so the way that we move temp from the beginning to the next one is saying, okay, now you're going to point to whatever's after you. So this is also an important thing in so there are exceptions to this, but in the programming languages that you most likely know or will imminently know, assignments work from right to left, right? If we've got some number x equals 5, we assign the thing on the right, 5, to the variable x, right? That's how it works. This is important to know, especially because we're working with some maybe tricky things on the right-hand side and the left-hand side. So temp.getNext, let's look at our node class. So temp is a node. Our getNext method returns a node. So we just say, okay, I don't want to be here anymore. I want to be there. So we just set temp equal to what temp.getNext gives us. And so that says, now I don't point here. Now I point here. Yeah.
There's nothing next. What is it?
Yeah. So let's say temp is here. And we say temp equals temp.getNext. GetNext is null. And so that would mean that temp is now pointing to null. So we've gone past the edge of the list. And this is something to keep in mind. You'll see it in the code a lot that it's checking, like, is the next thing null or not? Because you can't say like null dot get next. You can't do that because null doesn't know what get next means. So that's not allowed. So there's checks for that to make sure that's not happening. So yeah, so we can take any links that are available. And so if we've got the next pointer, then we can always just say, give me the next one. And then by assignment, point there instead. So overwrite where is currently working and say, I'm going to work there now. Okay, so the head of the list, that's where we start. So we've got a special pointer in our linked list class to keep track of that. And that's our anchor. So let's go to the linked list class and see that. So you'll see I've got a field called head, and it's of type node T. So that says this is where we start. Sometimes, especially if you're working with doubly linked lists, you may have an additional pointer, typically called the tail, so like head and tail. And the tail keeps track of the end of the list. And one of the reasons that you do that is so that if you need to go all the way back here, because you can't use indices, anytime you want to go through the list, you have to do this whole process of write a for loop and say temp equals temp.getNext and go through till you get to the very end. If you don't want to do that, then you have a tail. So that way you could start either at the beginning or at the end. Any questions so far? Yeah.
You start at the end, does like the get next go from like B to C?
So if we had a previous pointer, then we could say temp equals temp dot get prev if we had that functionality. If we're only in a singly linked list though, like what we have in the lab, you don't have that. And so that's why we maybe don't have a tail. Because remember in our river analogy, we can't go backwards at all. So if we're at C, this is also something to keep track of as we navigate inserting and deleting, where if we're at C, the only way to go back to B is to go to the head and start all over. All right, this is important. So remembering that in a singly linked list, we can't go backwards. We can only start over and keep better track of where we are. Okay, so for insertion, there's a couple of steps. So let's say we want to insert some data at a given position. So let's say we want to insert at position X. So in this example, we want to insert something right here so that our list will look like A, B, E, C, D. So currently it's A, B, C, D. And so we want to insert something between B and C. So the first step to get there, first we need to navigate to that spot because we can't use indices. So we do that whole thing of temp.getNext until we get to position X minus 1. So we want to go, because we can't go backwards, and we'll need to break some links and make sure everything points to the right thing, we want to stop one before the place where we want to insert. So we navigate temp up to X minus 1, which is B. The next step is to create this new node. So now we're like, okay, I've got my data. I'm going to create it and I'm going to stick my data in there. Then we say this node, I'm going to say it points to the thing at position X. So this happens first. And next, now we need to break this link from B to C and instead say B points to E. So for our, if we have things in our paper chain, we want to first add the new thing in and then like cut the old paper and glue it to the new one, right? And the reason that we do it in this order is if we glue B to E first, then we'd have to drop C. And then so in doing that, we lose C and D and the whole rest of the list. So the reason that we do it in that order is very specific. It's so that we don't lose anything. So this is a second. So we said E.setNext C, that does this link, and then set temp's pointer to the new node, which is temp.setNext. And we called it E. So that's how we insert something. The cases are maybe slightly different if we are either at the beginning or at the end. If we're at the end, what do we need to do to insert it? We don't need to break any links, yeah? Yeah, just like say, here's my new node. You point here now instead of no. So it's a little bit simplified. Let's say we want to create a new node at the beginning of the list. So we make the new node, set it to next pointer. Are we good? The answer is no. Because remember, we've got the anchor, the head of our list. And so if we just leave it as it is now, our anchor is the second chain and not the first one. We always want it to be the first one. So if that's the case, we need to say head's not here, now the head is here. So that's something to keep in mind as well. So there's generally 3 cases for these things. Either we're somewhere in the middle or we're at the beginning or end. And so if we're at the beginning and we've got the pointer to take care of, we need to make sure that we reassign that. Similarly, like if we were at the end and we had a tail variable, we need to say, nope, the tail's not D anymore. Now it's F or whatever we named that node. Right, so we need to update that as we go, if we need to. This is the slide I was looking for. So the way that we iterate, you'll see this in the code. You can use a for loop or a while loop. This code uses a for loop, where we have to start somewhere. And so we'll typically start at the head. And then we have some index that we want to count up to. And so like we use the same numbering systems. That's our choice because we're designers. If we really wanted to, we could say start counting at 1, or start counting at 5 million. That's a choice we make. The simplest choice is probably say this starts counting at 0. So we start at the head, and then we have the line of temp equals temp.get next to move us along until our condition, until we get there. So that's should not be new. We have the same kind of idea for how we do that. For a while loop, I wish I had written this down, but we can do this anyway. So we still need to start somewhere. So we say the temp is equal to the head. That's where we start. And so if we were doing this where we're navigating just before some variable IDX, so we'll typically also need a count starting at 0. And so we'll say while count is less than IDX. And typically we want to make sure that we haven't gone off the end of the list, because if we have like 4 things in our list and we're looking for thing 7, then that's bad. We don't want to go overboard. So we'll also see if temp is not null. So as long as temp isn't null and we haven't reached our count yet, then do the temp equals temp.get next, and then count plus plus. Right. So the same kind of idea, where we're still iterating through, and the way that we iterate, we have some loop of how many times are we doing this, and we have this, which actually moves us along. Yeah, so we take all the next links until we get there. If we need to, so let's say like you're looking to find something in the list, then we can first change how many spots we're looking for. We could say like go from here to the end to like size -1 or something. And then we can add as much logic as we need here. So like temp is pointing to a node. If we're looking for something, maybe we check, is the data for temp equal to the data we're looking for? So we can add logic. So this sort of structure of how we iterate, we can adapt for our needs. Okay, any questions on insertion or iteration so far? Okay, we're almost through. So for deletion, it's the same kind of, it's maybe a little bit easier than insertion, because for insertion, we need to set 2 links. But for deletion, so let's say we've got this node that goes 5, 10, 15, and 20, and we want to delete the thing, we want to delete 15. The simple way to do this is to just say, okay, now 10, you don't point to 15, you point to 20. So we just like bypass it. Let's go around it. Let's ignore it entirely. In a singly linked list, this is fine. So in a singly linked list, now we've got something like this. So if this is our main list, and maybe we've got something hanging on here. here's where references and scope come into play, right? So if we've got a pointer to keep track of the head of the list, we can always go from here down along the line. But if we don't have any back arrows, if we get here, there's no way to go back to this guy, the one that we said we'd delete. So this guy is essentially stranded. We can't access him. This works for singly linked lists. If we had a doubly linked list where there was that option, we would need to break that link. But for a singly linked list, we don't care. This is also where I typically bring up that Java has garbage collection, which is once we can't reach something, once we can't access it, then we should basically consider it gone. So Java does that automatically. We don't typically need to worry about it, but it's something you should know for linked lists, where once we get to this situation where 15 is stranded, and we could technically get from 15 to 20, but if we don't have any way to access 15 directly, because now this link is broken, then, oh well, sorry, 15, you're gone. So the way we do that bypass is we kind of chain these dot operations together. And so the way you read it is we're saying temp.setNext. So if this is temp, so in here it's prev, but if we had called it temp, so temp.setNext, so point to this thing. And so temp.getNext gives us this guy. And that's a node. And so we can say, give me the next one of that too. And that gives us 20. And so that's how we can do that bypassing. If we wanted to set it like 3 nodes away, what would we change? We wanted to bypass not just 1 node, but 2.
Get next one more time.
Yeah, so just add another one here, .get next. So yeah, so because temp.get next, you can add parentheses if you want, like this gives us a node. And so we can call get next on a node, because that's a method that a node knows what to do with. And then call get next on that. So that's how we delete something. Let's consider the cases where, let's say we want to delete 20. So still we iterate to position x minus 1, which would be, let's consider the case where 15 hasn't been deleted. So if we go to 15, how do we delete 20? Going to be the same kind of idea, right? So the thing after 20 is just null. So we can say 15 point to null now. So we can still do get next. That's still allowed. So, so we went over middle. If we're at the end, this works. What if we want to delete the first thing in our list? Yeah. Or
I was just gonna suggest, I mean, no, just like head. Yeah.
Head what?
Don't know. Like, from the unit head.
Yeah.
Can we possibly change the head profile?
Yeah. So like we can say head equals head dot get next. And so that'll strand 5. Yeah, again, caveat that this works if you're a singly linked list where we can just ignore it. If we were in a doubly linked list, we would need to set the backlink to null. Questions on that? Okay. Right, okay, so we went over these we need to make sure that we're getting all the cases where we're keeping track of what are we doing at the beginning, at the middle, or at the end. And we're making sure along the way that we don't lose the rest of the list. Because if maybe like for these examples where they're very small lists, 4 or 5 things, maybe it's not as big of a deal to us. But if the list was very long, like 1,000 things, and we lose everything 3 on, that's a problem. So we need to make sure that we're careful as we go so that we don't lose the rest. Okay, so lab 6 comes in 2 parts. So today we're going to go over the code, which is understand the implementation that I give you. And in the next class, we'll actually do lab 6. So the instructions I'm improving, where once we know how linked lists work, I'm going to ask you to come up with a solution for this complex operation and then implement it. Okay. So some notes for what my implementation looks like. We talked about parameterization. So it can hold any sort of thing that's in there as long as everything is the same type. So it can hold combination locks as long as every node has a combo lock. Okay. Sounds good so far? Okay. Let's go to the assignment. Okay, so I'm going to I haven't decided if I want the groups for today to be the same as for next time. Maybe assume that they will be, and if that changes, I'll let you know. So here's the UML diagram for the linked list class. And I've got a link to the code here. Remember, you don't need to clone it, just having it open in another tab is fine. Your job is to post outline this code. So I give you code, there's maybe some comments as we go to kind of summarize, but I would like a better summary. So say, what is this method doing? So what is this constructor doing? It calls copy over. What is copy over doing? And so having you trace through the code and see what's going on here. So some of the things you'll see, let's see, we've got find, we've got insert. We talked about insertion. And so maybe this is a good place to start to see, we're checking that it's out of bounds. Why do we need to do that? What are we doing here? So maybe a switch case is new to you. So maybe look that up. So today you're not necessarily writing code. You're going to be writing a summary of code. Does that make sense? So writing like plain English, here's what this code is doing. So maybe like more enhanced comments of this is code that I wrote. I want to know what you understand about it. So yeah, so write an outline. Here's what it's doing. Write it in as plain English as you can and be as descriptive as you can. So maybe I say this inserts a node at position 1 minus the index. That's great. What does that mean? How does that happen? So write it in words. So I'm going to pair us up. So we're going to try something today where I would like in your pair or maybe group of 3, depending on how the math works out, one person should be the driver. The other should be the navigator. So the driver is the one who's typing. So like pull up a Google Doc or a Word document and is typing, here's the outline. Here's what that looks like. And then the navigators are looking at the code and saying, oh, this is what this is doing. So this is like when you're on a road trip, the driver is actually executing things and the navigator is planning ahead and saying, do this, do that. So we'll try that for today to kind of, yeah, to help you kind of structure your group. Does anybody have any questions on how that works? Okay. So yeah, so the navigator pulls up the code on their computer. The driver creates a document and make a bullet point for each, maybe each thing in the class. I will say you don't have to be very verbose, but I would like some maybe sentence or two, if it's simple, then a few words. If it's more complex, then more words. And then at the end of your documents, I also want you to say, here's what insights you have. Here's what I thought about this code. Is it easy to understand? Is it difficult to understand? Are there things that you didn't recognize that you now know how to do? Are there things that you would have done differently? I didn't like how you did it this way. I would have structured it this way. And then submit the document to Canvas. I will note, please don't use AI for this because it's an important skill to be able to read code and then talk about it and try and summarize what's happening. And so if you give it to AI, then it does the work for you, and that's not the goal of this assignment. All right, are we clear? Okay.